Okay, so like I said the other day, the lecture notes are up there on Canvas. So if you want to use those lecture notes, they're pretty much filled in, except for some of those examples like I talked about before that will work out in class, or again anything I just kind of scribble on the page that comes to the top of my head, which I'll be honest with you, it does happen. Yeah, so I will kind of just go off and kind of do some examples that maybe aren't in the notes. So if you have a separate paper to add those in or something like that, it'd be good. I try on some of the handouts to kind of have, a couple of extra spots in there, maybe for you to use those things, but we will do some of those things. We're going to start with chapter 1, and we're not going to necessarily go over every part of chapter 1. As I mentioned last time, chapter 1 has a lot of sort of math review, which again would probably be good if it's been a while since you've taken math, or you need some help with math and some of those operations. It also has some really good pictures and some information about using your calculator, which I think I might have mentioned last time, is an issue for a lot of people, kind of the punching it into the calculator part and stuff like that. So that's a really good thing to look over, and we might look at some of that today. I definitely will, as we go through the chapters, take some time to hopefully make sure everybody knows how to properly punch certain things into your calculator. And as I mentioned last time, it's a good idea to have your calculator at all times, both for lecture and lab, because we'll do a lot of examples in here. And then obviously in lab, you will need to do some problems and stuff like that. So the other important thing in terms of the calculator, as I talked about as well, is to make sure that it is the one that you're going to use on a quiz and an exam. Yeah, so find one that you're happy with, find one that you think will work good for you. It again just needs to be a basic sort of calculator and stuff like that. All right, so we're gonna get into here chapter 1, which is a little bit about chemistry, like I said, and also again, it's about like little introduction to math and review of some math things. So chemistry really does affect sort of every area of our life. Obviously, pharmaceuticals, for example, makeup, food, all these things are basically, involve chemistry to one extent or another. Forensic sciences as well, right? Crime scenes, investigations, all those type of things, involve really chemistry. So when we talk about chemistry, it really is the study of matter. And matter is really anything that occupies space and has mass. So it's really anything that really occupies space and has mass. So pretty much, everything that you could kind of think of is what we will see here, in terms of matter. And chemistry really deals with a lot of how that matter changes. How does it change in a chemical reaction? How does it change as it goes from different states, say from solid to liquid to gas, and vice versa? When we talk about matter, it really, there is kind of three states of matter that we talk about. We have solid, and typically speaking, in the solid state, everybody is pretty well packed in there, pretty tight to one another. So everybody is in there, not a lot of movement, doesn't have a lot of energy. Usually solids, as we'll talk about, is usually very dense. They have fixed shape, like this desk, and that's because everything is relatively packed in there tight. When we get to the liquid state, we still have everybody packed in there relatively tight, but one of the major sort of differences is we actually have a little bit more energy happening. So what happens here is, because there's a little bit more energy, those molecules or atoms are able to actually move past each other. And that's why when we think about a liquid, right, it is, bless you, it is fluid, right? And you could pour it, right? And it will flow and stuff like that. And that's because there's a little bit more energy. Everybody could kind of move past each other. They're not really locked into place like we typically see in the solid state. And again, we get this sort of fluid state that occurs. When we get to the third state of matter, which is gas, at that point, we have pretty much broken apart everybody. So everybody is broken apart from one another. They have a lot of energy. They're flying around. As we'll talk about when we get to the gas chapter, as they're moving around, there's going to be a lot of collisions that occur. Collisions with the container, for example, collisions with anything else flying around in that container as well. And that's what we associate pressure with. And with those sort of collisions that occur, and as we'll talk about in the gas chapter, more collisions usually results in more pressure occurring. So a lot of what we look at in terms of chemistry deals with these three states. It also deals with how we sometimes transition from one state to the next. So when I go from solid to liquid, that is the process of, what do you think it is? It is the process of, when I take an ice cube out, what happens to it? It starts to melt, right? So that is the process of melting. I feel bad about my melted ice cube that's now liquid water. I put it back in the freezer, right? And it will become a solid. That is the process of freezing as you go from liquid back to solid. When I have liquid, some liquid water on the cooktop there, I want to make a little pasta for dinner, right? I put some fire underneath it. It starts to boil, right? And as it starts to boil, it goes from the liquid state to steam, right? All that steam you see coming off of the water in the pot. The process of going from liquid to gas is the process of evaporation or vaporization, depending on which way you want to do that. And what happens when we go from gas back to liquid, that is the process of condensation. For example, if you taken a hot shower with all that steam, typically when you look at your mirror when you get out, it is full of water, right? Because the mirror is nice and cool, hits that hot steam, hits it, it goes through condensation. The steam is really water in the gas phase, and then it kind of cools back down and comes back to the liquid phase, which is why it's all kind of watery there on the thing. Is there a question? Yeah. That's a very good one. Yeah. So these are exactly which I think we'll talk about in maybe the third chapter, but they are definitely physical changes. And that's because the three examples that we just used there, ice, liquid water, and steam, they are all still fundamentally H2O. They're all still water, basically. So that basically means there hasn't made anything new. And that's really the hallmark of a physical change. Basically, what you start with and what you end with is still fundamentally the exact same thing. Yeah. Now, we also can, and through these processes here, since we got the little diagram going, we could go from the solid state skipping the liquid state. And that is what is known as sublimation. Yeah. And sublimation is just that. We go directly from solid, skip the liquid mess, and go right to the gas phase. Probably an example that you may be familiar with is dry ice. So if you ever seen dry ice, use dry ice. By the way, dry ice is not water. By the way, it is carbon dioxide, is CO2. But dry ice will go from the solid state under our normal temperatures and pressures and shoot right over to the gas phase. It will never go into the liquid phase. For reasons we don't get into this class, you would need an enormous amount of pressure to force it to get there, about 5 times normal pressure to get dry ice to kind of go into the liquid phase. So it will not do that under normal conditions. It will just skip right on over into the gas phase. Now, we could also obviously go from gas back to solid. I'm assuming we could do that because I put an arrow. That's probably a good idea that we could do that. And it's the same idea. This is what is known as deposition. Like you're depositing something on something. Maybe you've seen a picture of a CD or DVD these days. I think they may still sell them, I suppose. But they're really shiny on top. That's how they get them really shiny. They go through a deposition sort of process and deposit the metals on there, which makes them really, really sort of shiny. So these are really the three different phases that we see a lot in chemistry, these are sometimes referred to as the 6 transitions that occur between the different phases. And what we deal a lot with in chemistry is this, a lot of physical changes. Obviously, we deal with a lot of chemical changes as well, or chemical reactions, but a lot we deal with these sort of transitions. While we're talking about it, does melting and freezing occur at the same temperature or a different temperature? What do you think? So assume the pressure is the same. Does it occur at the same temperature or different temperature? It occurs actually at the same temperature. So melting and freezing really occurs at the same temperature. And depending on what you're talking about, so for example, water, that is 0 degrees Celsius. That's the normal melting point or freezing point of water. And the same thing with evaporation and condensation. It actually also occurs at the same temperature. And for water, that is 100 degrees Celsius, which is the normal boiling point. So how do we know which way we're going to go? It really has to do with energy and what type of energy or what you're doing at those points as to what's going to happen. So when we talk about energy, which is also a really big aspect of chemistry as well, when we go from solid to liquid to gas, would I need to put energy in to do that, or do I have to remove energy to do that, you think? You would have to put energy in. A really simple example of that is what I said earlier. When you take an ice cube out of the freezer, what happens to it? It just starts to melt, right? And that is because heat flows from hot to cold. So when you take that cold ice cube out into room temperature, the air around it is hotter than the ice cube. All the energy from the air then goes to the ice cube, causing it to melt, right? You have your pot of liquid water that you want to boil. You put a fire underneath it, right? And we put a fire underneath it, it starts to boil, making it go from liquid water to steam, which again is still water, but changing phases. So all these processes, as you go from solid to liquid to gas, these are all processes where energy is absorbed. And in chemistry, when we have energy being absorbed, those are what are referred to as an endothermic process. So any type of process in chemistry where energy is being absorbed is an endothermic process. The opposite would be true if we looked at sort of the backwards arrangement of that. If we're going from gas back to liquid, back to solid, those are all processes going in that direction, which requires energy to be released. And if you think about it, we have gas molecules that are flying around really fast with a lot of energy. So what happens is as they release their energy, they're no longer going to be flying around with a lot of energy. So when they come in contact with other gas molecules, they don't have enough energy to escape each other. So they kind of stick together and then they kind of drop into the liquid phase. You continue to remove energy from it. They then have no energy to move past each other. They no longer become a liquid. They lock into basically a solid state at that point. And that is the process of what is known as being a exothermic process. So exothermics, anytime energy is released. By the way, we talked about the ice cube melting. That's also why the water freezes when you put it into the freezer. I know people don't do it anymore, but years ago, people used to put water in a tray to make ice cubes, right? They put water in the tray, they put it into the freezer. When you put that room temperature water into the freezer, at this point, the water is hotter than the air in the freezer. All the energy and heat from the water that's in the tray leaves it, allowing it now to basically freeze, right? And stuff like that. Any questions on any of that there? Okay. So energy is also a tremendous big part of chemistry, and we'll have a chapter about energy and some energy aspects. Chapter 3 a little bit later on. Matter, as I mentioned before, again, is anything that occupies space and has mass. So everything there is pretty much matter. It's really the stuff that makes up everything. And like I said, I'm going to kind of skip through some things in this chapter. So let's talk a little bit about the scientific method here. And the scientific method is a method that's used a lot in chemistry and science, obviously. And really, the scientific method kind of just all begins with where I put my pen. That's where it begins with. There it is. So it all begins with really usually an observation. And what happens is maybe you observe something, maybe somebody else observes something that makes you think, like, why did that happen? Right. And what we want to do next is kind of come up with an idea to try to explain maybe what we observed. And that's what's sometimes referred to as a hypothesis. And a hypothesis is really a important sort of explanation of observations. And really, sort of in science, a lot of times when you do a hypothesis, you do want one that is kind of testable. So something you could do some type of experimentation with. And that's usually what happens. We have these observations, we try to form a hypothesis to explain why we saw what we saw. We want to have something that we could test, so we then go and do some type of experimentation. The result of that is usually you will kind of maybe get into a vicious circle of more observations. Maybe observations you expected. Unfortunately, in a lot of cases, usually observations you didn't expect. And if you're doing this work for somebody, you tell them and they go, great, that was really interesting. You know what you should do? You should do a bunch more experiments, right? And they go send you to do more work, basically, is what they would typically will tell you to do. So it can be this sort of loop as you make observations. Maybe you revise your hypothesis, you do some more experimentations. But hopefully, at some point, it will lead to one of two things. Hopefully, it may lead to a theory or it may lead to a law. And hopefully, at the end of these experimentations, we kind of hit one of those two things, a theory or a law. And there is a difference between them. So, a theory is really something that kind of explains what went on or what's going on. Is it correct in all aspects? It may not be, but it may be correct at that point in some aspects. It may be disproven sort of later on through further experimentation. So, for example, the Bohr's model, our theory of the atom, works super well for hydrogen to explain what's going on with hydrogen. But you go any more electrons than hydrogen, which is pretty much everybody else, it doesn't work very well. So it works really well, and it doesn't work so well down the road. So there's Dalton's atomic theory, for example. Dalton's atomic theory at the time explained a bunch of ideas about atoms and what makes up atoms. And it was sort of correct at the time, but later sort of experiments found things like, as we'll talk about, isotopes and things like that, which sort of disproved not all aspects of his theory, but certain parts of his theory. So theories you could kind of think of as, a general explanation of sort of what's happening, kind of to the best of the ability of the information they have kind of at the time. It is not really set in stone. It could be kind of further revised down the road. And that is different than a law. A law is something that no matter what happens, it always happens the same way. So there's kind of like no exception. There's a law of conservation of mass, which means you do not create nor destroy mass along the way. So, for example, in a chemical reaction, if you started with 4 carbons and you ended with 4 carbons, those carbons may not be in the same things on both sides of the reaction, but you had 4 to start with, you had 4 to end with. And since carbon weighs about 12 grams, the mass of the carbon that you started with will be the same mass of the carbons you ended with, because you have 4 basically on each side of the deal. So we don't lose anything like that. Also, the law of conservation of energy. The law of conservation of energy tells us that we do not lose energy either, but energy can be basically transformed from one form to the next. So the idea of that is if somebody loses a certain amount of energy, say you did a chemical reaction that's exothermic, it's going to give off a bunch of energy from your beaker or wherever you're doing the reaction in. What's going to happen is somebody's going to basically absorb or collect all that energy that's being released. In the case of the beaker, it's probably the surrounding air is going to pick up all that energy, right? When you do like a combustion reaction, like you light a match or you light a Bunsen burner, you put your hand near it, don't put it on the flame, but you put it near the flame, right? You can feel the heat, right? Coming off. Yeah. So it's producing a certain amount of energy and it's giving it off to the surrounding air, right? Where hand would be picking it up and stuff like that. Same idea as well as like, your hand warmers and like hand coolers, I guess, as well, right? You break something, right? And it does a little chemical reaction. All of a sudden it feels hot in your hand or it feels cold in your hand, right? And that's really a transfer of energy. When you do that and you break it and it releases in an exothermic reaction all that energy and you're holding on to it, your hand picks up all that energy and you feel nice, warm, and toasty, right? Because it's picking up all that energy as that reaction is taking place. Same thing if you kind of broke that thing, kept it in your hand, and it was an endothermic reaction, like sucked out all the energy, right? The only thing it has to suck out the energy is from your hand. It's going to take all that energy out and absorb all that energy that you lose from your hand into whatever you're holding, and then will feel really cold to you in your hand. That transfer of energy will be equal. The amount of energy lost from your hand will be the same amount picked up by the object you're holding, or vice versa. The amount of energy released by that reaction will be the same amount of energy that you pick up in your hand. So these are laws of conservation of energy, and we have certain laws that no matter what happens, there's really kind of no deviation from it. Any questions on any of that there? Okay. So you do just need to know a little bit about scientific method. We're not going to go a lot questions or anything about it, but you should know the basic steps of it and what a hypothesis is, a law versus say a theory along the way. All right, so like I said, we're gonna kind of skip through some of this stuff here. You definitely should look it over, but uh, again, there's a lot of review type stuff in here. As I mentioned before, there's a couple of sections on math skills and chemistry. And again, you may want to definitely review it more than what we're going to probably go over here today. But make sure that you do. Again, just understanding a couple of things, obviously, places and numbers. So we have 2, 5, 1, 8 here. And the 2 is the thousands place. The 5 is the hundreds place. The 1 is the tens place. And the 8 is the ones place. So again, identifying those type of things are really important. Obviously, when we have decimal places as well, in this case, 6.407. The 4 there is the tens place, hundreds place for the 0, and the thousands place there for the 7th, or the 7 there at the end. All right. Also, when you're doing some basic math, a reminder, we do have sometimes negative numbers, right? We have positive numbers, and understanding how to treat those is also really important. So obviously a positive number, we typically don't write the positive sign with it. So like this example here, we typically just write 8. It's assumed if you don't see anything there that it is a positive number. Opposite though, if we do have a negative number, we do write the negative number. And remember that, if we are basically adding a positive number and a negative number, we're basically subtracting, right? So that's basically what's going to happen there. We're going to subtract kind of the negative number in that case. If we add 2 negative numbers, it's still going to be negative along the way. If we subtract a positive and negative, so if we are adding 2 negative numbers, you're going to end up with a negative, right? If you are have a positive minus a negative, That minus will then basically turn this into a positive, right? So two negatives make a positive, and you'll have positive and positive. So again, you want to make sure you understand how to do those type of things. So here, for example, a couple examples of negative and positive numbers. We're multiplying here two positive numbers. We end up with a positive 6. And here we're multiplying two negative numbers, which also gives us a positive number. So if you multiply two negative numbers, you get a positive number. You multiply a positive and a negative number, you get a negative number. So you keep that stuff in mind. Same sort of rules with dividing as well when you do that here. So here you can see positive, negative, negative number, positive, negative, negative number. It is important, the positives and the negatives in chemistry, especially, for example, when you're doing calculations, involving energy. One of the ways, and we'll talk a little bit about it, I think, in that chapter as well. One of the ways that we're able to determine, for example, if a reaction is, say, exothermic or endothermic, is it going to release energy or gain energy, is actually based on the sign. Is it a positive number or a negative number for energy associated with that reaction? So the number really doesn't matter, but it's actually the sign's really important. So it's really important, again, if you do some type of calculation, you end up with a negative number. It's not necessary that you did something wrong. It's actually important, the negative number and stuff like that. So you shouldn't just, for example, in chemistry, just disregard a negative number, thinking maybe you did something wrong. I'm not saying you didn't do something wrong. It's possible, I suppose. But, it may not be wrong. It may actually be correct with the negative numbers. So just keep that in mind as you go through it. Here, obviously, we have a fraction. So we're doing some division. Same idea. If we divide a couple of positive numbers, we get a positive number. We divide a couple of negative numbers, we do get a positive number as well. And same thing like the multiplication, we got one of each. We're going to end up with a negative number there if we have a positive and a negative number. There's our addition. So clearly, if we're adding two positives, we're good. We should get a positive number. If we're adding two negative numbers, we will get a negative number. Again, if we're adding basically a positive and a negative number, as I mentioned before, basically that's the same as 12 minus 15. It's the same idea, math as that. Again, it'll turn it basically into a subtraction. Now, more importantly, maybe the most important thing, or one of the most important things that you'll see in chapter 1, in my opinion, is kind of this thing. It's a good reference. As I mentioned before, lots of times in chemistry, I see it a lot on papers that people have things set up correctly. And then you look at the answer and go, like, how did they get to that answer, right? There's some type of disconnect between the work that's on the paper and how it was punched into the calculator. There's something goes wrong in between that. So using your calculator is really important, especially important in this class as well. And when we use our calculator, we want to make sure we use it correctly. So I'm going to actually skip the calculator and come back to it so that we could talk about it in relation to not graphs. We don't do very much graphs. In relation to actually scientific notation. So we'll come back to the calculator and kind of tie this into it as well. Scientific notation is probably the most important thing out of this chapter. And that is something that you do need to know how to do. So scientific notation in general is this formula here, which is n times 10 to the n. And this first n is a number between 1 and 10, okay? So it cannot be less than 1 to do proper scientific notation. It actually cannot be 10 or above. So it's got to be kind of less than 10, but it can be 1. So anywhere from 1 to just under 10, that first number can be. Times 10 to the little n here, this will either be a positive or negative number. And that really is dependent on which way you need to move the decimal point to get to a number between 1 and 10. So that's basically which way you got to go to get to a number between 1 and 10. And it will either be positive or negative depending on which way you got to do that. Why do we use scientific notations? Well, we use scientific notation because in certain cases, you come across numbers that have just a ton of zeros. They're really, really big, for example, or really, really small. So if you had something like, how many atoms there are in 1 mole of something, that's like 602.200000000. I lost track already of how many. And that's the whole idea there. You're going to probably lose track of all those zeros that you probably have. You try to use it in its kind of positional notation or regular form. Or if you have a really small number, like, 0.0000, a whole bunch of zeros and some numbers. So we use scientific notation to handle really large numbers and really small numbers as well. So for example, if we had 3, 2, 5, 6, 7, and we wanted to write this guy in scientific notation, what we would do in this particular case is, although there is not a decimal point written in the number, typically we assume it's at the end there. So again, even if it's not written, we kind of assume it's at the end. So we want to move the decimal point whichever way is going to get us the important part here, which is a number between 1 and 10. So if I go one place, that's like 3,000. So that is not a number between 1 and 10. If I go 2 places, that's 325. That is still not between 1 and 10. If I go one more, that's 32.5, which is not a number between 1 and 10. I go one more, now I'm at 3.256. That is a number between 1 and 10. So this would be 3.256.7 times 10, and I lost track, 1, 2, 3, 4 places to the left, times 10 to the 4th. This would be a positive exponent because we moved the decimal place to the left. Or if you want to remember it this way, it's a positive exponent when the number is a large number above 1, basically. Yeah, so that is basically the way that you would move it. Now, if we had something like 0.004320, for example, and we wanted to turn this into scientific notation, in this case, we would have to move it one place. That is not a number between 1 and 10. 2 places, that's 0.4, not a number between 1 and 10. One more place. And that's going to give us 4.320 times 10 to the negative 1, 2, 3. I think I went 1, 2, 3. There we go, minus 3. This is a negative exponent because we did move the decimal place to the right, or it's a small number. So a way you can remember that, basically less than 1 will be a negative exponent. Question on that there. Yeah. So we will talk about what to do with that in the next chapter. I'll preview it here right now. It has to do with what's known as significant figures. And when you turn a number, say from sometimes referred to as positional notation, just regular form, decimal form, if you will, into scientific notation, or if you go from scientific notation back to decimal form, you never want to lose any significant figures because they're important. So if we look at the number just quickly, they're all significant, and we'll explain that obviously in the next chapter. All 5 of those numbers are actually significant, and that's why we would not round in this case any of those numbers. Otherwise, we lost some significant figures, and that wouldn't be good. And it's the same reason for the guy on the bottom. Starting with the 4, and then the 3 and the 2 and the 0, those are all significant figures, and that's why we actually kept the 0 at the end of it there and didn't drop it off. And again, we'll get into that. They, for some reason, do scientific notation in chapter 1 here, and then significant figures in chapter 2. So we'll merge back into that in a second. There was another hand. Was that kind of similar question, or did you? The four, if we're talking about this one here, is basically how many places you have to move the decimal point to get to a number between 1 and 10. So in that particular case, if we start back here, we assume it's here. We had to go basically 1 spot, 2 spots, 3 spots, and 4 spots to get to that number between 1 and 10. And it's the same for the 3 to here. The 3 is how many places we had to go to get to 1 to 10, and we had to go 1, 2, and 3. In the case of the bottom one, it was actually written for us, so we knew exactly which way we had to move it in that case. Yeah. Other questions? Okay, so as you can see here, if we wanted to get this into scientific notation, we got to go 1, 2, 3, 4, 5, and 6 places. That gives us our 8 times 10 to the minus 6 in this case. And again, in this case, only the 8 significant, which is why we don't add zeros either for the same reason. Here we have 100,000. We assume that we are here. So 1, 2, 3, 4, 5 places, large number, 1 times 10 to the 5th. Now, although we kind of previewed there a little bit about significant figures, when you do write a number in scientific notation, every number that comes before the times 10 part, so basically this part here, every number that comes before that times 10 part is a significant figure. So if you see a number that's written in scientific notation, like I said, when we get to chapter 2, we'll talk exactly what significant figures are. For this time being, they're basically important numbers. You shouldn't lose them, basically, is what that means. They're always going to be significant figures. So the reason why we may use scientific notation and the reason why you may want to write a number in scientific notation is you may need to give an answer to the proper number of significant figures. And again, in chapter 2, we'll talk about calculations and doing that. And the only way that you could possibly do that is to write it in scientific notation. There's no way you could do it in like regular form, decimal form. There's no possible way. There are certain numbers, depending on how many significant figures you need for an answer. There is just no way to do it without writing in scientific notation. The reason why scientific notation is good for that is, let's just say, for example, I needed 2 significant figures. Now I have 2 significant figures. Let's say I needed 3. I could write 1.20 times 10 to the 2. Now I have 3 significant figures. So you can almost control how many significant figures a number has by writing it in scientific notation. And that's really useful for it, especially when we get into calculations where you got to give your answer in proper number of significant figures. Do you have to give every answer in scientific notation? I don't need you to do that. You will need to give every answer to the proper number of digits, significant figures. And again, that might require you to do so. Unless the instructions specifically say give the answer in scientific notation, you don't necessarily have to do it. But you can absolutely do it either way if you wanted to. Now, if we do have a number that is in scientific notation, 1.20 times 10 to the 3, and we want to turn it back into just decimal form, we would do the opposite. So the way I would look at this is that's a positive 3, which means my number is actually large, right? So I need to move that decimal point from the 1.2, whichever way is going to make that number large number, right? And not a small number. If I move my decimal to the left, will my number be large or small? Yeah, it's going to go left. So in this case, when we're going from scientific notation back to sort of decimal form, we will need to go to the right, 1, 2, and 3. And in this case, we would have to actually add a 0 here, and we would end up with 1200 in this case, right? Now, if I had 3.2 times 10 to the minus 3, same idea here. When I see that minus 3 up there on top, I know it's going to be a small number. So again, I want to take my 3.2 and I want to move it whichever way is going to get me back to a smaller number. Once again, we would actually need to go this way, right, to get to a small number, because we're going to go to the left and basically add zeros. So we would go 1, 2, and 3 and add some zeros in there to do so. So we will end up with 0.0032. as our number. By the way, when you do write a decimal number, speaking of doing things sort of properly, it is really important to include that 0 before the decimal point. That is because that will prevent hopefully numbers from running together. If you just write like 0.0032 and you got another number in front, before you know it, you're not really sure, what number is which. So it's not a good idea to do that. You should always put the kind of 0 before the decimal point so that everything is basically easier to see. Any questions on that there? Yeah. All right. So let's talk a little bit about. That's a good idea. Let's talk a little bit about, what we could do with scientific notation. You can, if you wanted to, for example, do it by hand without a calculator. And just so you know, if you are adding numbers that are written in scientific notation, whatever they may be, typically, if the times 10 part is the same, the times 10 part will stay the same. So this will be 10 to the 2, and all you have to do is just add these guys together, basically. Same idea if you're going to subtract those. Let me do a different number there, times 10 to the 2 minus 1 times 10 to the 2. Same idea, if these guys are basically the same, you could just subtract the front number and then do it times 10 to the 2. So if you're going to do it old school, which I don't know why you would do that anymore with calculators, but if you're going to add or subtract, what you might want to do first is make sure the exponents are the same and adjust them to the same exponents, and then you could just simply add or subtract the front numbers and keep the exponents the same. When you multiply exponents, you basically add them together. So if you're going to do a little of this action here, you basically will add those exponents together. So it then will be something like to the 4th there as you would do that. If you're going to divide, you basically would subtract the exponents in this particular case. So this would end up being something like times 10 to the 4th by adding those exponents. If you're going to divide exponents, let me just do this, divided by this. You basically will subtract those and you'll end up with basically 10 to the 1 when it's all said and done. So that's sort of how you do it old school, but nobody wants to do that. So let's now talk about our calculators, which is probably, dare I say, more important than knowing how to write it, which you should know how to write it, but knowing how to punch it into your calculator is really important. So when we look at our calculators, which maybe we'll go back to those slides there that has some calculators on them. There we go, maybe. So when we look at our calculators, you want to make sure that you, actually, I think I got better ones this way, I think. Maybe, or not. I'll just use it here. So when you look at your calculator, there's a few buttons that are really important. There is actually an exponent button on most people's calculator, and it either looks like an EE button, it may look like an EXP button, or if you have some of the newer calculators they started making, and these I would say is specifically almost like a two-tone calculator in terms of color. There's like a main color and the outside is like white or something like that, or a different type of color. I think I just saw one. Something like that calculator right there. And they usually have like that two-tone type color. You might have this arrangement in terms of buttons, which is actually a times 10 to the n. And you will usually have like a little wheel type of thing on your calculator as well towards the top right of it. These are actually your exponent buttons. And these we're going to talk about in a second how to use them here. But these are definitely the buttons you want to use when you're doing a number in scientific notation. In addition, another really important button is the negative button. And on most people's calculators, it looks like that, or it may look like this. So those are the two sort of common sort of change the sign. I call them negative buttons, but it kind of change the sign of whatever you're doing. These two buttons are really important, especially when you're typing numbers in scientific notation into your calculator. So for example, if we had this number 6.25 times 10 to the minus 4, and we wanted to properly punch this into our calculator, this is really what we should do. We should take 6.25. Now, I'm going to first talk about if you have one of these two buttons here. And I would say on most people's calculators, if you're looking for these buttons, most people's calculators, that button is right around here, kind of middle left, or bottom right is usually where you can find those. Sometimes you may need to hit like a shift button or second button, and it's on another button in this area to sort of find those. The negative button oftentimes are towards the bottom or sometimes kind of right around here as well. That's kind of where you'll find those buttons. So if you're one of those two buttons, you're going to play 6.25, you're going to actually hit your exponent button. And what you should see on your calculator at this point is probably 6.25. And on some people's calculators, it will pop up an E. Or on some people's calculators, it'll go 6.25 and maybe pop up a couple of zeros up on top, or a combination of like 10 and a couple of zeros kind of up on top. And that's usually what will happen. When you hit this button here, the exponent button, that button represents the times 10 part of the number. So you do not need to hit the multiplication button. You do not need to hit any other button there. And if you are hitting the multiplication button while you're trying to type a number in scientific notation into your calculator, you are doing it wrong and you will get probably the wrong answer. By the way, the other popular button people like to use for scientific notation that you should not use is the log button, because on most people's calculators it's got something that looks like scientific notation above it. That's actually the inverse log. You don't want to use that either in this situation. So you should not use that button for sure. All right, so once you do that, what is left to punch in for this number is actually the negative and the 4. So you would punch in next the negative button, whichever one you got, and 4. And basically what that will do is it puts you a negative 4. This will change to like a negative 4. And that is the proper way to punch a number into your calculator in scientific notation and hopefully get the right answer. Obviously, we would then do something with it, multiply it by a number, subtract it, add it to a number, divide it by a number. Now, if you have these buttons here, which is more that two-tone type calculator, not a big deal, except you got to do a little bit more work when you punch numbers in scientific notation into your calculator to get the right answer. So you pretty much have to, if you have this combination, this kind of two-tone calculator, you need to put every number that's going to be in scientific notation in parentheses in your calculators. So what you would do is, if you have this, you would actually start by opening a parentheses on your calculator. You would then hit 6.25. You would then hit your exponent button that looks like that. And what you should see on your calculator is a parentheses, 6.25. It will pop a times 10. You will now have a blinking cursor up there in the top right, blinking at you right about now. You will then do the rest of it just like the other one. You will hit your negative button and 4. And when you do that, you will have a parentheses 6.25 times 10 to the negative 4. And now you will have a blinking cursor to the right of the 4 at this point. This is where the will comes into play. If you try to close the parentheses with your cursor way up on top, you're going to get a nice error message on your calculator, so you can't do that. So you need to go to your little will that you have on there, and you actually want to hit the right-hand side of your will. That will bring your cursor back down. And now you will have parentheses 6.25 times 10 to the minus 4. Your cursor will be down. You now can close your parentheses. It will now give you a regular size closure there, and then you're good to go. Obviously, that's a lot of steps. It's just written out that way so you can see the steps. Obviously, if you get used to doing it, it's not going to take you all day to do it. But you have to do, obviously, a lot more steps, if you will, for it to be correct. If you do not use parentheses on that type of calculator, your calculator will separate your numbers incorrectly and it'll do the math incorrectly and you'll get the wrong answer. If you have one of these two buttons, you actually don't have to be super careful. You usually could be pretty sloppy and you'll still be okay. Not that one's better than the other, but you don't have to be usually as careful, especially if you have an EE button. You usually don't have to be super careful at all. You can kind of do it multiple ways and it'll kind of still come out correctly. Any questions on how to punch that in? Yeah. Yeah. Now on yours, just looking at it, because it's not two-tone, you probably don't need the parentheses. Okay. It's really, in my experience, and again, I don't know all calculators off the top of my head, but in my experience, it's really those kind of ones that have like a two-tone color. It has like a main color in the middle and the sides are a different color. There are some calculators that are more solid in color that have the will, but you actually on a lot of those don't actually have to put the parentheses on those. So it's more, I would say, if you have a kind of a dual color one, that's usually the one with the will that you kind of have to do the parentheses. So if you try to do the parentheses with yours, you may get an error message or something. You got 1 over, you got like a fraction. Yeah. So if you get a fraction, which brings us to a different button as well on some people's calculator. I don't know if I have, but I might have a button on mine. Sometimes calculators will also give you an answer in a fraction, which you really don't want either. There's usually a button, I'm trying to see on mine where it's at. I almost want to say there's like a button that's like an S with an arrow to a D or something like that to the right. Uh, Let me see here. I think we got it on this one. Oh, I will if we're not sure, but there is a button that will turn that fraction into like a decimal number. You see it? It's usually to the right. As an X to D, I knew it was something to the D. So like an X to the D with like an arrow, that usually will turn your answer from a fraction into like a decimal regular number type of thing. Okay. So yeah, so that happens too as well with calculators. Sometimes people get and go like, I got a fraction. What am I supposed to do with that? But there's usually a button that you can push and it'll turn that fraction into like a decimal. I think that's what the D stands for, decimal. I don't know. And then the X maybe is the answer and stuff like that. Yeah, it will in this case because we didn't really do any calculation. We just punched the number incorrectly. So if we were multiplying it by a number, we would get another number. Here, what we were just talking about right now is how to properly punch it in. So why don't we do that? Why don't we actually multiply or do some problems with a couple of numbers in scientific notation just to make sure you punch it in correctly. But yeah, if you do what we just did here, it may just give you the exact same thing you punched in, or it may turn it into a decimal depending on the number or something like that. But you haven't really done any math with that number. You just punch that in properly. So why don't we just make up some here? Why don't we do 3.25 times 10 to the minus 6, and let's divide it by 4.5 times 10 to the we'll go 7. And why don't you also do 4.3 times 10 to the minus 4, and we'll multiply it by 1.20 times 10 to the 5. All right, so punch those in properly into your calculator and see what answers you get. I'll do it as well since I just made it up, obviously. Yeah. You do not. So once again, if you have either that EE button or the EXP button, you don't need to parenthesis up the numbers. You do need to put them in correctly. If you have the one with the times 10 and the will we were talking about where you have to do the parentheses, you have to put each of those numbers in parentheses like we talked about. See how you're doing. So I'm gonna do something, I think. Let's see. We will talk about how to punch this in. So we'll start with the first one here. So if I want to punch it in, again, if you have either The EE button or the EXP button, this is how you should punch it in. You should go 3.25. You should then hit your exponent button, either the EE button or EXP button. You should then go with the negative button, and you should go 6. And that again would be the proper way to type that into your calculator for that. In this case, we're dividing next, right? So obviously you want to hit your division button. And then we want to type the other number in the exact same way. We're going to go with 4.5. We're going to hit our exponent button. Again, that exponent button takes care of this part, so no need to do multiplication button or anything like that. This is actually a positive exponent, which means we don't need the negative button on this one. We just need 7 and an equal. Yeah. Now, if you have the one with the will where you do have to put parentheses, I'm going to try to remember. You're going to go parentheses. You're going to go 3.25. Going to hit your exponent button. You're then going to hit your negative button. You're going to hit 6. You are then going to hit your will here. You're going to close the parentheses. You then will hit the divide button, open a parentheses, go 4.5, hit your exponent button. In this case, again, is positive, so we just need to hit 7. Once again, we got to do the will to bring our cursor back down and close the parentheses and hit equals. That should cover 99% of calculators, I think, hopefully. So now if I do that, 3.25 exponent negative 6 divided by 4.5 exponent 7, that's going to be on my calculator here. I didn't have something on it. 7.2, a bunch of 2s, 2, 2, 2, 2, 2, a bunch of 2s. I'm just going to round a little bit here, but it has a bunch of 2s really. And actually, let me put them on 1, 2, 3. Thank you very much. So a bunch of 2s. And on my calculator, I have E minus 14. I get that. So that's sort of what my window looks like. Yeah. Now it's really important when you get your answer here, and your calculator may have a times 10 at the end there, but it's really important when you get your calculator, obviously, to round. So we're going to round a little bit. But when you give your answer, this would be times 10 to the negative 14. That is what the E represents here. Again, just like when you punch it in, the E represents the times 10 part. When you actually write the answer, it does need to be written as times 10, not E. So don't write E as your answer. Don't forget this part. I can't tell you how many people on their calculator just ignore the far right-hand side there and forget the exponent part. They just write the front part of the number. So don't forget that. It depends on your calculator. Some people's calculator may at the end there pop a 10 and you'll have your negative 14 like way up here. So it kind of depends on your calculator. But if your answer is in scientific notation, you want to make sure you don't forget it over there. Some calculators will actually give you like almost like a space between like the front number, and then they'll have like maybe like a minus 14, and that space is to indicate like the times 10 part. So you want to make sure that when you give your answer, you don't miss the kind of times 10 part when you're kind of giving the answer, and you do want to give it as times 10, not E. So you should never write an answer in scientific notation with the E, even though we punch it into calculators, Excel and stuff like that. You should always write it as times 10. Any questions on that? Yeah. By that should be the answer that you end up with in this case. So again, we're dividing, right? So in this case, you take minus 6 minus 7, right? So that's minus 13. But when we divide these numbers, it kind of rolls it one more spot because the front part will roll it, and you got to be a number between 1 and 10. So it rolls the exponent one more, if that sort of answers your question. All right, let's take a look at the bottom one here. 4.3. Again, we're going to go exponent button. We're going to go negative, and we're going to go 4. And again, that is the proper way there to punch this number in. We're multiplying in this case. We're going to hit the multiplication button. 1.2, once again, exponent button. And this is a positive exponent, so just 5 and equals. Once again, if you have the will, you need to parenthesis it up. Yeah, 4.3, exponent button, negative button, 4 will hit the right side, close the parentheses, multiplication button, open parentheses, 1.2 times 10 to the n, 5 will to bring your cursor back down, close the parentheses, hit equals. You do all that good stuff there. Hopefully 4.3 to the negative 4 times 1.2 to the 5. Going to actually give you, in this case, 51.6 in this case on your calculator. Also, a really important thing, sometimes your calculator does not give you an answer in scientific notation. By the way, it will also not give you your answer to the correct number of significant figures when we get to chapter 2 as well. You could write scientific notation. If I want scientific notation on this, we're going to go one more place to the left there, right? So 5.16 times 10 to the 1 would be scientific notation if I wanted to write that. Again, a number between 1 and 10. Question how to punch it into your calculator, which I would say is probably, I think I changed the page there, probably more important in some cases than writing it into notation. Any questions? All right, so make sure you know how to do that. If you're not sure still where your exponent button is at some point, come see me with your calculator. Yeah, we'll figure it out together on your specific one. Any questions on that there? I think we're going to maybe take a 10-minute break here, stretch your legs there, come on back. Okay, any questions on anything we've been talking about here? Very good. So again, like I said, if you're not sure how to do scientific notation on your calculator, at some point, just come see me. We'll figure out your button. So we're going to actually move on, I think, to chapter 2. And like I said before, there's a lot of review in chapter 1. You should definitely go through it. And like that math review, calculator type stuff, if that's helpful, definitely make sure that you know how to do it. Really, the main thing I would say kind of out of chapter 1 is knowing scientific notation, how to write it, how to go from scientific notation to decimal form to scientific notation. More importantly, what we were talking about there at the end, how to properly punch that thing into your calculator, and maybe a little bit about the scientific method would be good as well. The stuff that we talked about, matter and stuff like that, you do need to know, but I think if I'm not mistaken, we'll kind of hit it again there in chapter 3, but that stuff eventually you'll kind of need to know. But those are really the main things, definitely the scientific notation, calculator, how to use it is kind of the main thing. So we're going to kind of roll into chapter 2, kind of get into the main stuff of the class. So in this chapter, we're going to talk about measurements and really get into some of those questions you were kind of asking a little bit earlier in chapter 1. We're going to talk about significant figures. We're going to talk about calculations with significant figures. Before we do that, we will talk about how to properly take a measurement and really where significant figures come from. We will then talk about in this chapter conversions and dimensional analysis, which is a really big topic in terms of how you should show your work in chemistry and how you should work out problems. And then we'll finish it all up there with a little talk about density and stuff like that. So let's get into sort of chapter 2 here and measurements. So one of the most important things, definitely in chemistry and in science as well, is when you take a measurement, it is really important, the units part of it. So for example, if I said, hey, I have 100, what am I talking about? I have no idea. I could have $100, which would be awesome. I could have 100 pennies, still not bad, I suppose. Could have 100 apples. If you like apples, gonna make some pies. Maybe that's all right as well. But we really don't know, really what that means because we have really no frame of reference to what that number means. So whenever you take a measurement, and lots of people don't do this, you should always have a number and you should always have a unit associated with it so that when you do something like that, oh, I go 100 grams. Now I know I have 100 grams of something, which is actually a mass. as we'll talk about as well here, it's also really important to understand what that unit means, right? So when you say something, it is correct in the sense of when you tell somebody, I have 100 milliliters of mass. That is incorrect because milliliters is a volume, right? And grams, though, is a mass. So you want to also have a relationship in your head of when I see that unit, what does it represent? Is it like a mass? Is it a volume? Does it represent something? So we have units, and really, when we talk about units, there's kind of two types of units that we come across. There is what is sometimes referred to as the English units or the US units, sometimes referred to, which is kind of what we use here in the US. And, pretty much everybody else in the world there rolls with the metric system. So there's kind of the US, or sometimes referred to as the English set of units, and we have the metric system. And depending on which system you're using, they obviously do use different sort of symbols, right? So this is meters, which is metric. Here in the US, right, we use inches. And the metric countries, when they weigh you, even here, sometimes they still weigh you, I think, in kilograms. But, they use kilograms, but here we look at pounds, right, when we're doing weighing and stuff like that. When you look at your car speedometer, right, it's miles per hour, and then there's usually a little thing that says kilometers per hour, right, in case you happen to be driving over there in Europe or something like that. So, or a metric sort of country. So we have these two units, and you could imagine that if people are using different units and the world gets a little bit smaller in terms of people doing business with each other, if we're doing business here in the US and we're using US units or English units, and you're doing some business there in Europe and they're using the metric system, that could be really problematic, especially if you're building something and you're doing measurements in inches and they're doing measurements in meters or centimeters. That's not so great, right? So you get the wrong sizing, things don't fit correctly, and you have problems. So believe it or not, in 1916, they had a big conference on weights and measures. Sounds like fun. And they came up with basically this idea that in science, perhaps we should have kind of a standard unit that we use. And in chemistry and most sciences, that standard unit is what is referred to as the SI unit, or the International System of Units. Who really won there? Well, frankly, it's kind of based off the metric system. So the metric system sort of won there. But the SI unit we have for different types of measurements, things like length, things like volume, things like temperature and mass. So we have these different sort of units that are used. And again, you'll sometimes see the SI unit for mass is this, or the SI unit for temperature is this. And again, it's really based off the metric system. And those are sort of the units that we use a lot in chemistry. So speaking of that, in chemistry, the metric unit there is volume liters, which is a very common one. But cubic meters is the SI system for volume. For length, the SI system is the meter. For mass, it is the kilogram for the SI unit. Temperature is one that you might not be familiar with. It is Kelvin. Kelvin used to be called the absolute temperature scale, later renamed for a guy named Kelvin, I'm assuming, right? So that is where that came from. I will say, if you're not familiar with Kelvin, you will be very familiar with Kelvin by the time we're done here in this class, because especially in chemistry, pretty much if you're using a temperature in a calculation, it's almost a no-brainer that that thing needs to be in Kelvin in most formulas. And a lot of times, as we'll talk about, you're going to be doing a conversion between Celsius and Kelvin. And it's almost all chemistry formulas that you come across, usually the temperature has to be in Kelvin. So that's something that we use a lot for sure in chemistry. For time is seconds. So as I mentioned before, it's also really important to have an understanding of what these units, again, represent. Are you talking, like I said before, a mass, a volume, a temperature, and so forth? So let's talk a little bit about volume. Volume is the amount of space that's occupied by a substance. It's measured in meters cubed. Common units, though, that we do use a lot in chemistry is liters, which is abbreviated with an L. milliliters, which is ml. The relationship between those is there is 1,000 milliliters in 1 liter. So that is definitely a conversion that pops up a lot in chemistry, that kind of conversion between those. I would say in most cases, milliliters and liters are probably going to be your most common volume unit that you come across. I would say probably 9 times out of 10, if you're using type of equipment in the laboratory to make a measurement, it most likely is going to be in milliliters. And a lot of times in formulas, if you need to use a volume, a lot of times it does need to be converted to liters. So those are very, very common. A way that we can measure volume is to use something like this. This is what is known as a graduated cylinder. It has different markings, and we could take an actual volume reading by just obviously filling the solution into the graduated cylinder and taking it. Graduated cylinders are really good pieces of equipment to take volume readings. Really lousy pieces of equipment to take volume readings are beakers. Beakers are really terrible sort of things to use to take volume reading. So keep that in mind in the lab when it tells you to measure out like 5 milliliters. Don't use a beaker. Yes, use something like a graduated cylinder. On a beaker, as we'll talk about, sometimes you think you're out the line and you're nowhere near it if you actually measure out. By the way, when we do take a reading of a volume, we always look for the meniscus, which is the curvature of the liquid that occurs when you put a liquid in a glass container. A lot of times the meniscus will look like a U, and we always read from the bottom of the meniscus. They won't always look like a U. Sometimes certain things can actually go the opposite way. Like mercury is an example of that. You actually would read from the top. I would say though 9 times out of 10 or even more than that, your meniscus will look like on the right there like a U. The reason for that we'll talk about in another chapter, but really the reason for that is the attractive forces between the liquid and the glass in the container are stronger than the attractive forces between the liquid and itself. So what happens through capillary action is those guys in contact with the sides starts to rise up the container and create this kind of U that you see. That's why you read from the bottom of the meniscus, because in the bottom of the meniscus, that's in the middle, not touching the walls. And that's really truly where the volume is. If it didn't have that attractive force to the container, the volume would be back down where it is in the middle and the bottom. And that's why you take a reading there. Now, again, like I said, 1 liter is 1,000 milliliters. Definitely we use a lot. I would say all these do pop up. This one does sort of pop up. That's a quart, by the way. I'm not sure where the T went, but there should be a quart there. But definitely this one, as I mentioned before, 1 liter is 1,000 milliliters. Definitely something that we see a lot. Length, on the other hand, as I mentioned, is meters. And that is both the metric and the SI system. Meters, centimeters, kilometers are very common units. So centimeters, meters, kilometers are all very common sort of units that we see. There's 1,000 meters in a kilometer. There's 100 centimeters in a meter. Yeah. So those are some common sort of length conversions that we do. How do we get length conversions? Well, we use a ruler a lot of times, right, to measure length. By the way, we talked about volume there a second ago. You could actually take 3 length measurements together and to get a volume. So for example, if we measured a cube and took the length times the width times the height, and we measured each of them in centimeters, each of these individual measurements are length measurements. But when we multiply them together, we will actually get cubic centimeters, which is actually a volume. So if you take basically a measurement of a cube, length times the width times the height, and 3 length measurements and multiply them together, you actually get the volume of that solid object by doing so. But each of the individual ones are length measurements. By the way, 1 cubic centimeter, which is a volume, is the same as a milliliter. And perhaps in the medical field, it's the same as a cc as well, right? A cubic centimeter, give that person 5 cc's right before they die, right? So those like medicine I watch the medical shows occasionally, so they give you those type of things when they say those things. So for chemistry, for the most part, we don't use cc too much in here. We do use cubic centimeters written like this, but a cc is the same thing as a cubic centimeter. More so used a lot of times in sort of healthcare and that type of situation as well. Here are some conversions. Like I said, this one is definitely one. These other ones do pop up. This is something that you should know. That is the relationship between sort of the metric system and the English system, if you will. 1 inch is equal to exactly 2.54 centimeters. So that's an exact conversion. So if you look on a ruler where you have the 1 inch marking and you go straight down, you'll be about 2.54 centimeters on the bottom, right? So when we look at a ruler, right, we typically have up on top inches. On the bottom, we have centimeters, right? And the little dashes where the centimeters are what? They're millimeters, yeah? So the millimeters, 10 millimeters in a centimeter, right? So the little dashes on the bottom of the ruler where the centimeters are located are millimeters, and centimeters are the ones that are marked on the bottom, and inches are marked up on top on our typical ruler when you look at it. When we talk about mass, the mass of the object is measured as the quantity of matter it contains. There is a difference, by the way, between mass and weight. Mass is independent of the force of gravity, while weight is dependent on the force of gravity. So if you weigh yourself here versus the moon, because the gravity is different, your weight will be different, but the mass of yourself in both places will basically be the same. So typically speaking in chemistry, when you weigh something, which oftentimes confuses people, which we use here a balance to weigh things. That is what is referred to as a scale. It's a fancy word for it, I suppose. We use it to get the mass of an object. So you should refer to it as the mass of the object in chemistry when you go weigh something, not really the weight of it. And that is really this balance that we use a lot is something like that. Digital balances, by the way, as we'll talk about in general, digital displays, all the numbers are important, by the way. So if you use something in lab that is digital, you should always record all the numbers that are present. Yes, sir. Are you talking about density? Yeah, density is mass divided by the volume of an object. And we'll hit that towards the end of this chapter for sure. Yeah. Other questions? So some common mass equalities, like I said, 1,000 grams is a kilogram. This is a crossover from metric to English. 450, it's really like 453.6 grams is 1 pound. That is metric there in grams to English on pounds. That's also a conversion that comes up a lot in chemistry. That 454 is fine to use, equals 1 pound. Temperature, there are 3 different types of temperature scales that we come across. We have degrees Celsius, we have degrees Fahrenheit, and we have Kelvin. Now, the one major difference with Kelvin is there is no degree sign. So you do not say degrees Kelvin. It's like 273 Kelvin, for example, no degrees. You do degrees Celsius or degrees Fahrenheit. Fahrenheit is what we use like when we take our temperature, right? 98.6 or whatever it may be, degrees Fahrenheit. Celsius is what everybody else uses. And again, on thermometers. On the Celsius scale, for example, water freezes at 0 degrees Celsius and it boils at 100 degrees Celsius for water. On the Fahrenheit scale, it will freeze at 32 degrees Fahrenheit and it will boil at 212 degrees Fahrenheit. That is also the difference in terms of how we do conversions between those. And Kelvin is basically a conversion of 273. So how we calculate these, and I think we'll see it in a later chapter as well, but The one that we use the most is Kelvin. So if you want the temperature in Kelvin, you're going to take the temperature in Celsius and add 273 to it. The real number is 273.15. Most people leave the 0.15 off. I personally do. Some people want you to keep the 0.15. But that will convert your temperature from Celsius to Kelvin, which, as I mentioned before, probably outside of chapter 2, that's going to be our whatever chapter it really is, maybe chapter 3. That's going to be really the ones you're going to use the most. You're going to take things from Celsius to Kelvin. Obviously, if you need to go backwards, the temperature in Celsius would be the temperature in Kelvin minus 273. So basically just to reverse it there. While we're at it, the temperature in Fahrenheit is equal to 1.8 times the temperature in Celsius plus a 32. And if you want the temperature in Celsius, is the temperature in Fahrenheit minus 32 divided by 1.8. 1.8 you might be familiar with is 9/5, right? The fraction maybe you learned as well, same deal. By the way, 1.8 is the 180-degree difference on freezing to boiling. This is where that 1.8 actually comes from. And 273 comes from something we'll talk about in the gas chapter when we get there as well. So these are actually the formulas that you do need to know. They will probably not be provided for you to do some conversions. Like I said, I believe it's in chapter 3 where we'll do some examples and stuff on that, but these are technically the ones. But out of these, like I said before, probably these two are the ones you're going to use the most. And out of those two, that's probably going to be the one that you're going to use really the most along the way, which is going from Celsius to Kelvin. Definitely in class here in lecture, also in lab, because your thermometers in the laboratory are in Celsius. And if you have to do some type of calculation, you'll have to take your reading in Celsius and then convert it to Kelvin is typically very common what you have to do. Question on that there. Time is seconds. Dare I ask it? How many seconds are in a minute? 60 seconds in a minute, right? How many minutes in an hour? 60 minutes in an hour. How many hours in a day? Yeah, it's only 24. Not 60 that people like to put because they go 60, 60, and why not 60? That's way too many hours. 24, perhaps too many hours in a day. So 60, definitely not it. So obviously some of these things may not be provided for you. So hopefully some of these things you do know, but keep that in mind. That's a funny one, maybe not for the student, but sometimes it's funny. That does pop up a lot. And it happens because people are doing that like 60 seconds in a minute, 60 minutes in an hour, 60 hours in a day. So just, only 24 on that one. All right. So for each of these, let's talk about what type of measurement we're talking about here. We got basically kilograms, which means we're talking about kilograms is a mass, right? Meters is a length, right? Grams is a mass as well, and liters is a volume, right? Perfect. And again, that recognition is really important so that you understand what you're talking about. Obviously, there we talked about these SI units. Again, meters cubed is a volume. So like I said before, sometimes people like meters cubed or decimeters cubed, which is a liter. Again, if you basically take any length measurement and cube it in the sense of sort of a cube, it will give you a volume. Kilograms for our mass, again, meters and Kelvin there for our temperature. All right, so take a moment, and for each of these, which one is the SI unit going on here? Okay, so let's take a look. So we're looking for the SI unit here. So I'm going to go with which one? The first one is the SI unit? Meters. Sounds good. How about for B? It is kilograms. Yep. And temperature, Kelvin. Yep. Sounds good. Any questions on those there? Cop. All right, so let's talk a little bit about measured numbers and taking measurements, which is a really important thing here, and really significant figures. And so let's talk about measurements. When you take a measurement, as I mentioned before, you should always have the number and the unit, but more importantly, you need to be able to take the measurement correctly. And whenever you take a measurement, there is always some degree of estimation that has to happen. There's some degree of uncertainty in your measurement. Pretty much there's some degree of guessing that's going to happen there. The amount of guessing that you're going to do is based on the equipment that you're using. Some are better than others. Again, a beaker, a lot worse than, say, a graduated cylinder in terms of taking volume. So let's talk about how we properly take a measurement. So let's take a ruler here, and we'll draw it here. So 1, 2, connected dots. We'll call these centimeters. And let's just say we wanted to measure my arrow in this particular case. So whenever you take any type of measurement, there's always kind of two sets of numbers that you should look for on the scale of the equipment that you're using. I personally call them the large sort of markings and the small markings. Now, the large markings are the ones that actually usually will have numbers on them. Yeah. The smaller markings typically don't have numbers on them. They're between those things. So if we look at this here on my ruler, my large markings are these two, right? And if I subtract those two, that's how much centimeters is the difference between them. It is 2 minus 1 is 1 centimeter difference, right? So between the large markings, that represents basically 1 centimeter of length, basically, or distance. Now, the other markings that we want to figure out is how many small markings do we have between those two large markings? Now, when you count the small markings between them, it's important to count them correctly. And the correct way to count it is start counting past the last large marking. So in this case, on the left here, 1 is my last large marking. I would start counting the smaller guys here. That would be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. We stop counting at the next large marking. So we start counting after the large marking, and then we keep going until we hit the next large marking. So we have 10 of these small markings. That's between our large marking that represents 1 centimeter. That means each of the small markings represents how much distance? 0.1 centimeters. I could get that by taking 1 and dividing it by 10, by the way, which is the number of small markings there are. Yeah. That means that if I come to this guy, this is 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, and 2 as we go across there to our next large marking. First off, any questions? Yeah. We're going to talk about how to properly take it in 1 second right now, actually. So to answer your question is, when everybody looks at that, right, or whenever you take any type of measurement, there should always be some numbers that no matter who looks at it, everybody should agree, right? So as you correctly said, I think, everybody should agree that my arrow is at least 1.3, right? So it's definitely not less than 1.3, right? It's not out the 1.4, but it's at least 1.3. And because it is at least that much, and those are certain no matter who looks at it, everybody should agree, you should record those. And that is what is sometimes referred to as recording all the certain numbers. And when you take a measurement, you should always record all the certain numbers. The problem is, as you also mentioned, my arrow, maybe it's just because I'm a bad artist here, but my arrow is not exactly at 1.3, and it's not exactly at 1.4. This is where the uncertainty comes in. This is where the estimation comes in. Now, I may look at that and go, I think it's like halfway there, right? Between those two spots. Somebody else may look at it and go, I think you're crazy. I think it's nowhere near half. Maybe it's less, right? And somebody else may say, I think it's like closer to the 1.4, right? So that is where the uncertainty is. That's where the estimation is. So for example, if I hypothetically think, well, maybe the tip of it is just a hair past the half mark there. Maybe it's a 6. And I would obviously want to record my units as well, which would be centimeters. This is what is referred to as the first uncertain number. That is where I'm not really sure exactly, what it is, but I think it's kind of in that ballpark. And when you take a measurement, you should always record all the certain numbers plus the very first uncertain number. And that is how you take a proper measurement. That is also, when you do that, by the way, our good friends known as significant figures. So significant figures comes from measured numbers, where you record all the certain numbers plus the first uncertain number. The uncertainty, or the estimated digit here, in this case, is the 6. And what I'm saying is I think it's 1.36, but heck, it could be 1.37, might be 1.35. The uncertainty actually lies in that last digit. By the way, that would mean this number has how many significant figures? It would be 3, right? Because if it's a proper measurement, everything there is significant, right? So all the certain numbers plus the uncertain number. Question on that. Now, really important, you look at your scale because it may change. Well, maybe you see why I failed art 3 times. It's all right. All right. We'll go 20. Oh, milliliter action. We'll do our meniscus that we talked about, a little curvature of the liquid going on there. Really bad meniscus drawn. All right, so we're going to do our same thing. Large markings here. What is the large markings represent? How much? We have 20 here and 10. The difference there is 10. Yeah, so that is a 10 milliliter difference in the large markings. Once again, we want to figure out what the small markings represent. We want to count how many we got. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. In this case, each of the small markings represents how much? It does represent 1 milliliter. If you're not sure, take the large markings divided by the 10 smaller markings. 10 divided by 10 is 1 milliliter. That means this guy right here is 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. Yeah. I kind of like my bad meniscus there, but we'll draw it right about there. Yeah. So I'm going to take a reading here. Certainly it is at least what? So I changed the picture. Certainly it is at least what? How much? It is at least 15. That is definitely certain numbers, right? Again, we have a little estimation. Perhaps here again, you feel it's a little above half, right? So maybe you go with 8 milliliters, right? Certain numbers. Uncertain number, the first uncertain number. That would mean this number has how many significant figures in this case? It does have 3 significant figures. Yeah. By the way, it doesn't always have to be a 5 at the end. You could do 8s, you could do 5s, or you could do 5s if you think it is halfway there along the way. Again, it's really important to take the reading because let's just say we had this guy. Try my meniscus again. All right, on this one here, my large markings represents how much on this one? I got 20, I got 10. How much? 10 milliliters, the large markings, right? The large ones, yeah. In this case, our small markings. We have 1 small marking, 2 small markings, 3, 4, and 5. That means each of the small markings in this case represents 2 milliliters. Again, you can divide it by 5, right? Get you the 2 milliliters. Now that means that this marking here is actually 12. That's 14, 16, 18. We appreciate. There we go. We're going to go this way. Now when I look at my volume, it's between 14 and 16. What number comes between 14 and 16? 15, yeah? This number would have how many significant figures? It actually would have 2 significant figures. The uncertain number is the 5, yeah? It's the best you could do on this scale. The reason it's the best you could do on this scale is it goes from 14 to 16. In that little space, there's no way to know exactly where 14 stops and 15 starts, right? There's not enough room. When you just have like one difference between markings, right? Halfway is halfway, right? You kind of know it's halfway. You don't know in this case. So the best you could do on this is actually to the whole number in this particular case. So it's really important to look at your scaling because it can be different depending on the piece of equipment that you're using. And it may not even be the same as the person standing next to you in lab because they might have bought it from a different vendor that has different markings on the scales and stuff like that. Now, typically speaking, you can take a reading properly to one more place to the right of the smallest marking. This is an example where you can't do that. But here, smallest marking was 1 milliliter. We could go one more place to the right to take the actual measurement. On our first one, smallest marking was the first decimal place. We could take the reading to one more place to the right of the smallest marking. Question on that. Now, if you're not sure how far you can take the reading to, and you want a way to know, like, how far should I really take this reading? And you're very confident on what the small markings represent. Like you're very confident, hey, this thing represents 0.1 milliliter, 0.1 centimeters, the small marking. You could take the small marking and divide it by 2. This will give you plus or minus 0.05 centimeters. That's how many decimal places? 2. How many decimal places do we take the measurement to? 2, yeah? If you take this guy, smallest marking is 1 milliliter divided by 2, gives you plus or minus 0.5 milliliters. How many decimal places? 1. How many decimal places do we take the reading to? 1, yeah? Even works on the weird one, like we had on the next page. Take the smallest marking divided by 2 is plus or minus 1 milliliter. That's a whole number, right? Took the reading to a whole number. So that's how you could figure out the uncertainty in a measurement if you want. If you're not 100% sure, you can follow the general rule of going one more place to the right, and that usually works in pretty much all cases. But if you're very confident, I know for sure what each of the little markings represent, all you have to do is divide it by 2, and however far that goes, 1 decimal place, 2 decimal places, no decimal places, that is exactly how far your reading should go to. Questions on that there? One last thing here before we wrap it up, why we got it all drawn here. Let us say that this arrow here on this exact same scale that we had going on, let's say I concentrated really, really hard and I went right on the 1.3 marking, right? Not so much of an arrow anymore, but we'll go with what we got going on there. All right. I can record 1.3 centimeters, right? 1.30 centimeters. Is there a difference in terms of how I record it? Does it matter? The answer is probably does, or I wouldn't be asking the question. So it does matter. Let's just talk about significant figure wise. Yeah. This number here, how many significant figures would it have? Would have 2 significant figures. The uncertain number would be which number? It would be the 3. So what you're saying in this case is I think it's 1.3 centimeters, but maybe it's like 1.4, maybe it's 1.2. That means you're thinking it's somewhere in that area. Is it anywhere near that area? That is a lot of uncertainty, right? That you should not have based on this scale. This number has how many significant figures? Would have 3 significant figures. The uncertain number would be? It is the 0. It is always the last significant figure there, right? So that is our uncertain number. So what you're saying in this measurement is, I think it's 1.30 centimeters, but maybe it's 1.29, maybe it's 1.31. When we look at that, that's like right there, right? So that is pretty reasonable based on the equipment that we have. So sometimes people think it doesn't matter if you lop off a significant figure like we were talking about earlier. It does matter because if you take off that 0, like we did over there on the left, You just made your measurement a lot worse than it should be. You made it a lot crappier of a measurement than it should be based on the equipment you're using. Also really important is the opposite extreme, which is I want to be more scientific. So let me just lay up a couple more zeros because that looks chemistry-like. That now means that guy has how many significant figures? 6. I don't know. I just kept writing numbers, but it does have 6. The uncertain digit would actually be this guy, right? Now you just made this measurement way better than it ever could be on that scale, right? So you shouldn't go the other way either. You should always go to the proper number of digits, because putting extra zeros actually means that your measurement is way better than it should be. And lopping off zeros or numbers, you're actually making it a lot worse. So if you find yourself, which happens a lot, especially in lab, like you're dead on a number. I always love when people go weigh out things. They're always dead on the number, always. They don't want to record anything else. It's 52 always. Point something? No, it was 52. I stood there all day to measure it out. If you hit right on a number and you have the ability to go to one more digit, you need to add the 0 to maintain the proper number of significant figures, or you have a really bad measurement. Any questions on that?